That was the thermal wind relationship, which of course we did in great detail on Thursday. And that mid-latitude jet stream is going to have troughs and ridges. Remember how we talked about when the jet stream turns in, it's heading to the south and it turns back, makes a left turn and heads off to the north? We call that a trough. When the jet stream is headed to the north and then it makes a right turn and goes back down towards the south, that was a ridge. The jet stream is going to have these troughs and ridges. And those troughs and ridges are going to lead to patterns of divergence aloft. And the divergence aloft is going to cause the cyclone. Remembering that the whole reason we're doing this is we're trying to explain why the cyclones are there. So this is what this PowerPoint is about. It's about explaining this process as to how we get these cyclones through this three-step process. Now just to reflect, because it's been not only all spring break, but even a week before spring break, since we last talked about these jet streams, remember both in the northern hemisphere and in the southern hemisphere we have two jet streams. We have a subtropical jet stream that sits at about 25, 30 degrees north. It's important too, but it is not really what's affecting our weather. Our weather is more affected by the mid-latitude jet stream, which sits more about 45 degrees north. It's drawn on this particular plot a little bit too far north, in my opinion. I mean, we don't live in central Canada. But you get the idea. It's farther to the north. It's more over us. And if you remember, the reason why it was there was because of the thermal wind relationship. This is just a slide that I stole from that PowerPoint, which is available to you on Blue Line, where we explained that when you had a polar front at the surface, we had these differences in thickness between the cold side and the warm side of the front that caused these huge pressure gradient forces aloft that resulted in a big strong wind that we called the mid-latitude jet stream. So, that jet stream can sit up there aloft, and it can be two different ways. We talked about this. We can use two different adjectives to describe the mid-latitude jet stream. We talked about this at that time. We can describe the mid-latitude jet stream as being zonal. Zonal meaning that it just flows from west to east. And other times the jet stream is meridional. Meridional being the adjective that we use to describe it when it meanders to the north and the south in the form of troughs and ridges. And we talked about the fact that explaining why it has these two different ways it can flow is a little beyond the scope of the class. But it's related to the same reasons why, like sometimes smoke rises from a cigarette in a nice smooth stream, and other times it meanders, it swings back and forth in little spirals and so on. It's the same reason why rivers sometimes flow in a straight line and sometimes they meander in the oxbows. It's beyond, it takes math beyond the level of this course to explain why that is, but that it is no problem. But either way, wherever you've got your polar jets, your mid-latitude jet stream, you know you've got to have the polar front directly below it. That's what the thermal wind relationship is telling us. Now I'm just drawing a front here like a blue line. I'm not telling you whether it's a warm front, cold front, stationary front, or whatever. But ooh, here's some fancy PowerPoint voodoo. See how it's down there at the surface underneath the jet stream? Aloft, we've got the jet stream. It's up near the tropopause. At the surface, we've got this front. And the thermal wind relationship tells us wherever we've got that polar front, right above there, we should, I mean, it doesn't have to be like to the inch directly above it, but it needs to be in that general area. So, that jet stream, when it is zonal, is boring. Zonal flow is important for certain things in meteorology, but it doesn't have anything to do with cold fronts and warm fronts and stationary fronts and cyclones and so on. So we're going to forget about situations where the jet stream is zonal, because most of the time, frankly, in our part of the world, the jet stream is meridional. And it flows in these troughs and ridges. Remember right here the notation that a trough is drawn as this dashed line, and it's a place where the jet stream was headed to the south and then makes a left turn and goes back to the north. And a ridge, which is drawn as this zigzag line, is the place where a jet stream was headed to the north, but then makes a right turn and starts heading back towards the south. Most of the time, in our part of the world, the jet stream has troughs and ridges in it. Now, we need a word that's going to describe what those troughs and ridges are doing. And that word is vorticity. Vorticity is an important idea in meteorology, because vorticity is a number that we often describe as being a number that describes the spin of the wind. Vorticity is actually more complicated than just spin. But spin and vorticity are closely related. And of course, so many things in meteorology are about spinning. Cyclones, anticyclones, hurricanes, tornadoes, dust devils. Lots of things are spinning in the atmosphere. And the number, vorticity is a number. It's something we can calculate based on the winds and so on. And vorticity is a number that describes how fast the spinning is happening. So for example, we can do the calculations and we could compute what the vorticity is over Omaha right now. It's fairly tricky. It takes some fancy math to do it. But it's possible. Computers can do it easily. And the vorticity calculations are defined so that a positive vorticity is rotation that is cyclonic or counterclockwise. So something like a cyclone, for example, has positive vorticity. So do troughs. Troughs have positive vorticity. Now, they aren't spinning the way that arrow is. I'm putting that arrow on there just sort of to help you visualize what's going on. The trough isn't spinning in the sense like the whole thing is going around. But if air is in the trough, it needs to turn as if it is going in a circle, right? It doesn't make it through the whole circle. It just makes it through part of the circle. But it needs to make that left turn. And that is positive vorticity. I mean, given time, it would go in a circle all the way around. Now, it would take it days. That's frankly a pretty damn big circle, right? It covers several states. But it could do it. So, troughs have positive vorticity. When we do the calculation that there's a trough over Omaha, we find out that over Omaha there's positive vorticity. In the same sort of way, ridges have negative vorticity. If we do the math and compute the winds and so on in a ridge, what we find out is, the winds aren't spinning like a top or something like that, but they are turning. They're turning as if they're trying to go in this great big circle. Now, again, it would take them days to make that whole circle. And they're not going to be there that long. They're going to go shooting through that jet stream over, a period of hours or something. But they're turning as if they were moving in that big circle. They have negative vorticity. That place in between the trough and the ridge has no vorticity. It's the straightaway. The vorticity is zero between the trough and the ridge because the flow is going straight. It's not turning to the left. It's not turning to the right. It is just going straight. Now that place may not sound like it's very interesting because the vorticity is zero, but on the other hand, it is an area where we have positive vorticity advection. Oh my God. What a term. We've used this word advection before. Like literally, the first unit of the course, maybe even like the second lecture, we used the word advection before. Advection is about moving stuff with the wind. When we were talking about advection in the first couple lectures of the course, what we were talking about was temperature advection. We were taking warm air in one place and we were moving it with winds, and then that warm air was someplace else. But actually you can advect anything with the winds. We often talk about like moisture advection in meteorology, where moist air is being moved by the winds to a dry place. Or where there might be other kinds of advection in meteorology. You can advect anything, including vorticity. Well, down here, in like the base of this trough, we have positive vorticity. Up here, between the trough and the ridge, we have no vorticity, which means that this area, the winds are bringing us air that has more vorticity than the air that's down. We have an area of positive vorticity advection. It is a place where the air doesn't have much vorticity now, but the winds are bringing air with more vorticity. For that matter, the area between the ridge and the trough is an area of negative vorticity advection. This area itself doesn't have very much vorticity, maybe even zero vorticity, but the air that's coming towards it has negative vorticity. So it's experiencing negative vorticity advection. Negative vorticity is being advected into the area. Okay. See why I think this is the hardest lecture of the year? Yeah. Okay. It does get, this is as bad as I think the course gets, in my opinion. It's hard. Maybe not as bad. No value judgments. Okay. So what exactly is this business